Welcome back to real time digital signal processing course. Today we will discuss about continue with our FFT. So, in the last class we discussed about FFT for fast computation, how it is going to help us in speeding up our computation from DFT, and then we saw that what are the quantization effects of our FFT in computation, and then how we are going to do the scaling. So, today we will talk about a little bit on computation aspects of DFT and then FFT with examples. So, we call discrete Fourier transform pair as analysis and synthesis equations. So, analysis equation is given by x of k is equal to n is equal to 0 to x of n e power minus j 2 pi n by n, where k is going 0 to n minus 1. So, we can represent this with the twiddle factors, and inverse DFT, as we know, it is IDFT, which is given by x of n. We have the scaling function 1 by n for k is equal to 0 to n minus 1 x of k into w n k. Here it is w n k, here it is going to be w n minus n k, what we will be taking it according to the twiddle factors. To derive this x of n, what we can do is we can substitute our x of k with this equation and then derive the thing. So, for this derivation, that x of n becomes x of n, and why we have the 1 by n scaling function also, you can refer to any of the digital signal processing book. So, which will give you how to derive our that is analysis substitution in our synthesis, get our x of n back. So, now we will see with a few examples. So, we first will determine the endpoint DFT of the following sequence for n greater than or equal to or length L, what we call it. So, x of n is equal to 1 in the 0 to less than or equal to n less than or equal to L minus 1, and which is going to be 0 otherwise. So, then we can represent our DFT of x of n up to length L minus 1. So, that is x of omega or x of k, what we can take it, which is going to be in this case we are assuming x of omega, that is DTFT, discrete time Fourier transform. Here the amplitudes are discrete and then our frequency is continuous. That is the reason why omega is there, which omega is going to vary 0 to 2 pi basically. Then DTFT is given as x of n into e power minus j omega n, and then when we substitute that, we have got x of n is equal to all ones. So, then what happens to that? N is equal to 0 to L minus 1 e power minus j omega n. So, this what we will be representing with sin omega L by 2 divided by sin omega by 2 into e power minus j omega L minus 1 divided by 2. So, what happens to our x of omega? So, this is what our equation is. I think something it must be boggling in your mind basically. We call this as a sinc function. So, x of k, if we calculate that in the DFT domain, this was in the DTFT. So, then what happens to this equation? Sin 2 pi k by n L divided by 2, and then here also sin 2 pi k by n divided by 2, and then this e power minus j 2 pi k by n into L minus 1 divided by 2. So, this is what we will be getting it if our x of n is we call it as a unity step function basically here. U of n, basically n is in this case L minus 1 length. So, then we will take up a simple example to see that how we are going to compute our DFT from a small example. So, what it says is we have to do the plot and calculate the magnitude plot the magnitude and phase spectrum of the sample data sequence, it is just 2001, okay, 4 point what we have to calculate. So, which was obtained using a sampling frequency of 20 kilohertz, and verify the DFT result using IDFT also, whatever DFT values we have got it, how to verify it. So, we have to do IDFT, then we have to get back the signal. So, we will see with the because it is the small value what we have taken the thing 4 bit. So, our x 0 what we will calculate first. So, for that n is equal to 0 to 3 x of n, because our k is equal to 0 in this case, correct. So, e power minus j will be 1. So, it is x of n. So, it is nothing but 2 plus 0 plus 1, which is equal to 3, which is magnitude is 3, and then it is at an angle of 0 degrees. And then we will calculate x of x 1 basically, n is equal to 0 to 3, and then x of n e power minus j. So, which is equal to what is it, x of n into e power minus j pi by 2, because it is n, capital N is equal to 4. So, which comes down to minus j pi by 2 into n basically. So, when you substitute the values for expand your summation, it is going to be first one is x of 0 is 2. So, it is going to be 2, and the other two values what we have taken for simplicity is 0, and then the last one is 1 when n is equal to 3. So, this becomes e power minus j 3 pi by 1. So, if you substitute for e power minus j in cos and sin, you will be seeing 2 plus cos 3 pi by 2 minus j sin 3 pi by 2. So, you will be getting this as 2 plus j. So, this is 0 and this is minus 1. So, it will be plus j, 2 plus j. So, when you calculate your magnitude, it is going to be 2.236 at an angle of 26.57 degrees. So, magnitude is computed with square root of real squared plus imaginary squared. Okay. So, that is the value you will get it, and then the angle will be tan inverse what you can see imaginary divided by your real. So, now calculate the x2 next stage. So, here also you will be seeing that 3 components are left out. It is going to be e power minus j 3 pi. So, it is going to be cos 3 pi minus j sin 3 pi. So, this comes out as you can see that it is going to be minus 1, and thus j term is 0. So, it becomes 2 minus 1, which is equal to 1. It is also 1 at an angle of 0 degrees. There are two ways of computing your x3. So, one is here what is shown is direct computation. So, what you arrive at is 2 minus j. So, this is at a 2.236 at an angle of minus 26.57 degrees. This is one method. The other one is you can use the periodicity property basically, and we know that x3 is equivalent to x1 conjugate. So, then what happens, I will be taking 2 and minus j. So, this is the way what you will be substituting. So, now we will see how the magnitude and phase response is going to look like. So, we have been given the sampling frequency Fs as 20 kilohertz, and then our n is 4. So, if I substitute Fs by n is nothing but 5 kilohertz. So, we will be seeing that f in the this thing x axis will have points of 0, 5, 10 and then 15 are the sampling frequencies. So, 4 points what we have to have our magnitude. Magnitude of our XR is going to be, we know that first one is 3 what we have got it, and second one is 2.236, 1 and then 2.236, and then we have calculated our angle also at these frequencies what you will be putting the angle. So, first one is at 0 is 0, and here we have a 26.737 degrees, and then the at 10 kilohertz we have 0, and at 15 kilohertz it has minus 26.57 degrees. This is how manually you can do the thing. So, we will seeing in the lab that how we can compute our magnitude and phase spectrum using either MATLAB or Code Composer Studio in using C language. So, now comes the thing. So, we have to verify whatever DFT values we have got it using the IDFT, that is inverse discrete Fourier transform, we are going to get back. So, we saw our analysis and synthesis equation. So, we will be making use of our synthesis equation, which is 1 by n is nothing but 1 by 4 in this case. So, our r will be varying between 0 to 3, x r what I have to put the thing. So, 1 by 4 into 3 plus 2 plus j plus 1 plus 2 minus j. So, you are already seeing that we have got back our original signal 2, that is first signal. So, this is going to be 3 plus 1, 4 divided by 4 is 3 plus 1 plus 4 plus what is the thing, we have it here you can see that this is 2 plus 2 is 4. So, 4 plus 4 is 8, what we have it, 8 by 4 is nothing but 2, plus j and minus j are getting cancelled in this case. So, now we will see x of 1. So, this is 1 by 4 r is equal to 0 to 3 r x r e power j 3 pi by 4 into r. So, which by expanding we are going to get it as, that is we will be getting it 1 by 4. So, we have to apply whatever DFT equation what we have got it values for them. 3 plus 2 plus j is the x 1, and then this is e power j pi by 2 plus e power j pi plus 2 minus j into e power j 3 pi by 2 in this case. So, when we expand this, so we are going to get it as 0. So, you can simplify this and you can see that the output is 0. So, how about x of 2 now? Same way what we have to work it out, substitute all the values and then you will be seeing that that also comes in 0. So, we know that using the symmetry property we can calculate x of 3 or manually by calculating to verify that you are going to get it 1 what you can see it. In this case we may not be able to compute the other value because it is 2001 is our value. So, we have to go with manual computation and you will be seeing the last stage what you have it is these are the values, by simplifying you get it as 1. So, you will be seeing that what was original case 2 0 0 here and 1 is the output. So, you will be seeing that DFT and then is analysis equation and IDFT is your synthesis. So, whatever value you have sent it you are getting it back basically. So, no compression is happening. So, why I am calling it as compression, sometimes we use our DFT for compression also, we can eliminate some of the low values and use in compression. Now, we will see that how we can use the previous one was decimation in time what we have used it using the FFT, that is fast Fourier transform using the butterfly structure. So, we have x of 0 and next one is x of 2, x of 1 and x of 3 are the 4 inputs what we have to give it. So, this you will be seeing that this is 2, x of 2 is 0 and x of 1 is 0 and then 1 is x of 3. So, it does not make the order reverse in this case because both of them we have 0. Then we have to calculate our this thing twiddle factors since n is equal to 4. So, our WR what we call it or WK which of the one we are conversant we will be using notations, it may little bit vary from 1 to 1. So, you can have one notation to use a thing. So, it becomes e power minus j 2 pi by n into r. So, which will be equivalent to, it is 2 pi by 4 r. So, which is nothing but e power minus j pi by 2 into r. So, we will see that W 0 always we know that it is 1. What is W 1 is nothing but putting r equal to 1, it is going to be e power minus j pi by 2. So, which is nothing but cos pi by 2 minus j sin pi by 2. So, we know cos pi by 2 is 0 and sin pi by 2 is 1. So, we are going to end up with minus j. So, these are the only twiddle factors what we need in computation. So, you will be putting this is 1 and this is minus j here. So, now do the simple multiplication and addition. So, what is my E 0 is nothing but x of 0 plus x of 2, okay, because we assume that this is 1. So, this is first one is x of 0 plus x of 2, which is nothing but 2 plus 0 is equal to 2. And then same way we will calculate E 1 here, which is nothing but x of 0 minus x of 2. So, you can see that how we are going with the thing, 2 minus 0 is equal to 2, and compute your O 0 and then O 1. This is the even part what it is and this is the odd part. So, what you will be getting 1 and then minus 1 in this case. So, these are the E 0, E 1, O 0, O 1. Now, we have to calculate because it is in this thing in order output x 0, x 1, x 2, x 3 what we have it. So, what is x 0? So, you will be seeing that x 0 is E 0 plus r x 1. So, it is 2 plus 1 is equal to 3 in this case, and then our x 1 is nothing but what we have E 1 fine, and then next minus j into O 1. So, that is what it is written. So, it is nothing but E 1 what we have is 2 plus minus j into O 1 is our thing is minus 1. So, this you will be getting it as 2 plus j, and you will be seeing the last one, if you substitute the thing you will get it as 2 minus j. So, x 3. So, whatever DFT you have seen that how difficult is to calculate here using the butterfly structure that is fast Fourier transform, we were able to do it in 2 steps to compute this values and one weight factor what we have to calculate and then put it in our butterfly structure. Now, we have to see that whether we are going to get back the results using FFT. So, what is it? Here x 0, x 1, x 2, x 3 are in sequence and our output will be out of order. X 0, that is bit reversed output what we will be getting it, x of 0, x of 2, x of 1 and x of 3. This we call it as decimation in frequency FFT. So, you will be seeing that we use this decimation in frequency, which is nothing but 1 by n, 1 by 4 what we have to put scale all of them, and then we have the butterfly whatever we used for DFT, which is going to be reversed in this case, as you can see the thing, and you will be marking this as A naught, A 1, B naught and B 1, and your this thing it is one coefficient here minus j conjugate, you will be getting it as plus j in this case. So, and then the rest of the butterfly you will be multiplying with minus 1 at the second part of it. The top one is going to have plus 1, as you can see the thing here plus 1 and here also plus 1. So, to this computation you will be seeing that you have to get back your output. So, we have A 0, A 1, B 0, B 1 first computed, and in the next case you will be calculating x of 0, x of 1, x of 2, x of 3. So, you are seeing that you are getting back 2 0 0 1 as your output. This is how both of them, decimation in time and decimation in frequency, work for your analysis and synthesis equivalent of DFT. Now, some of the important DFT properties we are seeing in this slide. So, the properties of DFT are different from those typical what we use it for discrete time Fourier series and discrete time Fourier transform, because they are circular in nature. So, that is they apply to the periodic repetition of the signal. Here you can have DTFS or DTFT. It can be this thing continuous signal minus infinity to infinity, whereas this uses a circular property. So, the first one is your notation. What is the time domain is represented as x of n, and frequency domain we represent it as x of k. So, the first one is the periodicity. So, x of n is equal to x of n plus capital N is nothing but this thing what we will be getting it x of n itself. So, which is equivalent to x of k plus x of n plus n in the frequency domain. And what is our linearity property? So, if x 1 is multiplied by any coefficient a 1 and x 2 multiplied by a 2, and if you add them, the result in frequency domain also it should be pre-multiplied by a 1 with respect to your frequency domain conversion, that is x 1 of k plus a 2 into x 2 of k. So, you can have the time reversal in your time domain. So, here it is going to be in the frequency domain, it is with respect to k what you are going to get the time reversal, and then you can have the circular time shift with respect to n. So, which is going to be reflected in your frequency domain as x of k into e power minus j 2 pi k L divided by n. Okay. And complex conjugate x conjugate of n is nothing but x conjugate of delayed function, that is n minus k. And if we do the circular convolution in the time domain, it is circular multiplication, as you will be seeing x 1 of k into x of k, x 2 of k. So, with respect to multiplication here, it becomes the convolution, circular convolution divided by scaling factor 1 by n. So, we know the Parseval's theorem. So, it is x 1 of n into y conjugate of n in the time domain. So, which is represented as 1 by n times k is equal to 0 to n minus 1 x of k into y conjugate of k. So, now we will see that how our hardware complexity using DFT and FFT in processor is going to reflect. So, as an example, DSP system is based on a floating point processor we have considered, and we say that it is capable of performing multiply and add instruction in one machine cycle, which is going to take 50 nanosecond. So, we have ignored in this case all IO operations. So, only we are looking into the computation aspects of our hardware. So, and we have next one what this it is defined is, that is, suppose that the system is used to implement the DFT directly and is required to output the DFT of 512 input sample points within an interval of 64 samples. That is, chunks of 64 samples are going to come out, and then what we have to do it, that is estimate the maximum sampling frequency if sine and cosine function are pre-computed and stored in the lookup table. So, we are not going to use the library function. So, we are saving little time. So, we will be calculating for 512 points, both sine and cos is computed and then kept in the table. So, we are using that to compute our DFT values. So, what is it? Using the DFT means we know that our either x of k or x r, what we can give it, n is equal to 0 to n minus 1 is 511, x of n into cos 2 pi by 512 r n minus j times n is equal to 0 to 511 x of n into sine of function 2 pi by 512 into r n. That is, we have split our e minus j into cos and sine function. So, we can see that this involves what is it? Phi 12 possible sine values and phi 12 possible cosine values are pre-computed. So, we are not taking the computation time of it because we have kept it in the lookup table. And then what happens to this now? So, frequency point requires phi 12 multiplications what we need it here, and then we need phi 11 additions. As you, I think something it should be coming n multiplications and n minus 1 additions what we needed for real and then imaginary part separately what we have to do it. Then it is order of n, if I take it 2 into phi 12 times what we want it, but what we have is k or r is going to go between 0 to phi 11. So, then what happens to this? It is 2 into phi 12 squared is our computation time to do our endpoint DFT. So, and then we have been given we are ignoring because multiplication and addition we are combining it, which is order of n squared. So, which takes 50 nanosecond what we have been given with. So, then this comes to about 26.21 millisecond, and we have been given that 64 samples chunks are going at a time. So, we will divide this 26.21 by 64, which gives us 0.4095 millisecond to do DFT for phi 12 length. And we know that maximum frequency what we can operate this circuit with is 1 by 4095 millisecond, which comes to about 2442 hertz or 2.442 kilohertz. So, this is what with the DFT. So, we will see with the FFT how we are going to compute it, except for stage 1 which is going to have only additions. So, each stage we have to do n by 2 complex multiplications, that is 256 complex multiplications, and we have discussed in the last class that each complex multiplication is going to take 4 real or ordinary multiplications. So, it becomes 4 into 256 multiplications, and we said addition is going to cause us 2 into 256 addition or subtractions. Fine. So, each complex addition is going to take 2 additions. So, that is the reason why 2 into 256 number of additions for the rest of the stages what we needed. So, if each complex multiplication is implemented by executing the multiply and add instructions, 4 times the number of multiply and add instructions required to execute at each stage, that is 4 into 256 what we wanted. It has to be executed. Okay. Further, the complex additions at each stage except stage 1 also require an addition of 2 into phi 12 times we said additions. So, what happens, the total number of computation stage is log 2 phi 12, which is nothing but 9 stages what we want, we have it. And we said stage 1 we do not need any complex multiplication in the thing. So, we need phi 12 additions in this case. So, if the execution time of addition instruction is assumed to be same as the multiply and add instruction. So, although we know that multiply may take little more time, but we are assuming at present it is going to have addition also same time. Then the computation time required for phi 12 point FFT what we are putting it. So, this is 4 into 256 plus 2 into phi 12 what we have it, or additions, as you can see the thing complex additions is nothing but 2 into phi 12 into, because the first stage we are having only additions which is assumed here phi 12 stages. So, n minus 1 stages, here 9 minus 1 is going to be 8. So, these are the ones which are causing our complex multiplication and then complex addition, which is separately taken into account. And then whatever complex addition with multiplication is coming, we are assuming that it is consumed in this. This is the other additions what we are showing it here. So, into 15 nanoseconds is going to give us 0.8448 millisecond, and then we said that it is 64 samples in this time period what we are outputting it. So, divide by that will give us 13.0 microsecond, and the maximum sampling frequency is going to be 1 by this, which is going to be 75.757 kilohertz. As you can see at 2 point some kilohertz in using DFT. Using FFT we are going to have 5.75 kilohertz. So, that is the comparison. So, you will be seeing that it is equivalent to 31-fold increase in the computation speed. So, now we will see that how we can implement FIR filter using FFT. So, we will be taking the DFT of our input signal and DFT of our coefficient, and then we have to do complex multiplication here XR into HR, and then we are going to take IDFT. So, this is what our circular convolution which is going to happen. So, how we are going to calculate this? If we are taking a 4 point, then we know that 4 squared is 16 what we are going to get the thing, and then multiplication and 4 into 4 minus 1 12 additions in the direct circular convolution for 4 point. Now, we are assuming the same thing and then trying to see that whether we are going to have 512 multiplications. So, here we will require 512 multiplications and 512 into 512 minus 1 whatever we said that additions for using DFT. So, we will be seeing that add instruction we can do it as 512 squared, basically what we are going to have it as it seen 512 squared, here it is 512 squared. So, what we say is 512 squared into 15 nanoseconds. So, it is going to be 13.11 millisecond what we needed. So, now we will see using FFT, although I am going to take it DFT and this thing. So, previously we calculated our each FFT needs 0.8448 millisecond, and then how many times I have to do it here 1, 2 and then 3 of them what I have to do it, because even IDFT is equivalent to DFT. So, we can compute it as 3 into 0.8448 millisecond plus we have to do this complex multiplication here. So, each complex multiplication as we know we have it as 4 normal multiplication 4 into 512 into 50. So, this is the additional. So, which runs at 2.6368 millisecond, and then we are calculating that is 3.11 millisecond in the thing. Here it is 2.6368 millisecond. So, we are still using all this complex method. Our FFT method is still 4.97 faster than the direct DFT. And one more thing one can keep in mind that because this is a predefined coefficients basically. So, I will not be recomputing every time, only our input signal is which is coming continuously. So, if we apply DFT and keep it pre-computed values here, so we can avoid one of the DFT online. So, then it becomes this one 2 into 0.448. So, which reduces to 1.792 millisecond compared to our 2.6368 millisecond. So, still we will be gaining with the thing. So, we will see in the next class, because we say that our x of n is continuous, how we will use the overlap add or save method to compute our FFT. Thank you.